Hi, this is group 42, and we're going to be talking about neuromorphic chips. So what are they? Neuromorphic chips are analog data processors that are modeled after the human brain, hence the word neuro. This is a new technology that is more advanced than the current von Neumann architecture, which follows a back and forth or linear pattern. Neuromorphic chips encode data in a series of bursts which attempt to mimic the synapses of the brain.
Neuromorphic computing takes significantly less time and space, theoretically, than traditional computing. This is due to the much more efficient computing ability than modern computer chips. The way neuromorphic chips are made are with an ANN, or artificial neural or neuron network. As you can see in the graphic on this page, there are multiple layers to how the computing process occurs, and this allows for decisions to be made more independently of the computer and less with human involvement. And the ANN, the artificial neural network, acts as human brain cells, or our neurons, which is vastly different than how traditional computing chips are made. It's a less of a linear path and more of a map.
Traditional computing to perform our neural network calculations? Well, there are a few reasons why neuromorphic chips are becoming increasingly prevalent in the realm of machine learning. The first is that neuromorphic chips do not run on a synchronous clock, as traditional computers do. They run asynchronously based on continuous input. In this way, the input is analog, which allows for the neuromorphic chip to really fine-tune any weights or biases that it may need to do during training. Specializing these chips in this way allows for them to bypass many overhead processes that occur in traditional computing and go straight to the training and learning of the neural network.
Based on the complexity of this technology, there's a wide range of application. Here are the three that we found most interesting. Due to their complexity, neuromorphic chips have potential for advancing a multitude of medical devices. For example, chips of this nature would be better able to control medicine administration devices. This is because, since these chips are not based on binary, there is a more continuous range of appropriate responses based on received biological signals. Artificial intelligence. Considering these chips would more closely resemble human synapses, there is a great potential for these chips in the realm of advancing the study of artificial intelligence. There would be faster computing potential, a wider response capability, and a greater capacity to resemble a human neuron, thus linking it to the artificial intelligence field. Imaging. While traditional computers communicate via electrical signals, neuromorphic chips would allow for the potential for imaging-based component communication. In this sense, components would transfer information using varying light signals. This would allow for faster data transmission, ultimately increasing data processing efficiency. Specifically, this technology would have wide applications to augmented reality technology, to name but one example.
There are a lot of uncertainties in the world right now. However, what is certain is that we are moving in a more digital direction. Technology won't just stop at our computers, televisions, or smartphones. It will find itself in many more realms of our lives in the coming years, from medical technology to autonomous cars to increasing intelligent smart assistants. As technology becomes more advanced and integrated, it will take on more human-like tasks. For those specialized tasks, we'll need chips that are up to the task of becoming more human-like and more flexible, not just computing zeros and ones. The differences of neurologic chips from traditional chips can provide the platform for these future developments. And just like how the first computing chips have completely changed the world, neuromorphic chips can have the same revolutionary impact in our computer lives. Thank you for watching our presentation.